spanning trees. This is a fundamental result in graph theory. If you have a connected graph, then it has a spanning tree. Here is a graph, and here you can see a subgraph, which is a tree, and it contains all the vertices, a spanning tree. So every connected graph has a spanning tree, and we may also try to count the number of spanning trees, and that's sometimes called the complexity of the graph. The number of spanning trees, I call it tau of g, and this has been considered for many years. One of the first results of spanning trees is Cayley's famous formula from 1889. The number of spanning trees in the complete graph with n vertices is simply n to the power n minus 2. It's not a deep result, but it's not completely trivial either. There are many, many proofs of this beautiful result. But that was not the first thing. Even earlier, in Kirchhoff's theory of electrical networks, you find spanning trees to play an important role, and I would like to talk about that today. So spanning trees in electrical networks. Let's go back to something we all learned in school. If you take two resistors and put them together in the following way, that's the same as having one resistor with this resistance. And you can also add two resistors in parallel. If they have resistance R1 and R2, then they can be replaced by one single resistor whose resistance is given by this formula. This is something we learned a long time ago. And this rule can, of course, be iterated. If you have some resistors here, you have 2 points. You should think of having a battery between S and T, and you can ask what is the effective resistance between S and T in this little network, and you can use these two rules successively. First, you can replace this by a single edge like this, and then these two you can think of as two resistors in series, and so on. So for many electrical networks, you can find what we call the effective resistance between these 2 points. For example, here we have the effective resistance between these two is this number R, where R is given in this way. But you cannot use this for all electrical networks. Those electrical networks for which this works is called the series parallel networks. And I think the name comes from this electrical network thing. Series parallel graphs, they are important in graph theory, but that's a very small, restricted class of graphs. There are graphs where you cannot use this rule, and here comes the smallest one. If you look at the graph you have up here, and we want to find the effective resistance between these 2 points S and T, then you cannot use the formula which I have just mentioned. You need something more. I've here written the right answer. This is the answer. And you'll see that if you put all these resistors equal to 1, then let's see what we get here in the denominator.
8.
We get 8. And 8 is the number of spanning trees up here. So there is a connection. And I'm going to prove this. I'm going to give proof of this formula, and many other formulas as well. In order to do that, I of course have to give a proper definition. When we learned these things in school, we were referring to physics, but now this will be purely mathematics. So we have to give a mathematical definition of the effective resistance. So what we do is the following. You take this network and you put what we call a battery here, and I'm going to explain what a battery is here. It has a V, and that's measured in volt, and then we look at the electric current which goes through the battery. We call that I, and then we make a definition. We define this effective resistance as the voltage divided by the current. That's the definition. I mean, in school we learned this as a physical fact, but we're not going to refer to physics, so now we want to do everything purely mathematically. But then, of course, you'll ask me, what do I mean by the electric current? Now I have to explain that mathematically. And I will. So here it comes. This is what we have given. A directed graph. This means that every edge has a direction. Every edge has a direction. There is one edge which is special. That's a battery. And we have a number associated with it. You should just think of this V as a positive number. And all the other edges also have a number associated with them, but they are different types of edges. Each other edge has a resistance R1, R2, that's also a positive number. And now, so this is what is given. Just a directed graph where every edge has a number associated with it. We now want to find the currents in all the edges, the electric currents in all the edges. This is the current in the special edge which we call a battery, and here we have the currents in all the other edges. What should they satisfy? They should satisfy, and here comes the actions. So this is the conditions, the basic conditions, Kirchhoff's rules, the current law, and the voltage law. They are very easy to explain. The current law, I just explained that using this picture. Suppose you have a vertex in the graph. Some edges will come in, some edges will go out, and then the condition for this vertex is that if you count all the incoming currents, so let's first count the outgoing currents, I2 plus I4, that's the outgoing currents, they should be equal to the incoming currents, which is I3 plus I5 plus I7, but I put them on the same sign of the equality sign so that I have a 0 here, and this means I have a linear equation. A linear equation. And all these linear equations should be satisfied. So if the graph has n vertices, there will be n equations here. One of them turns out to be redundant, but never mind about that. N equations. But this is not the whole story. Because there are many, many solutions to those equations. But also the following should be satisfied. If you take a cycle in the graph, and I've indicated a cycle here, and when I say cycle, I do not mean directed cycle. I mean the directions of the edges. I don't care about the directions on the edges. And also, you shouldn't, when you look at this direction, it does not mean that the current necessarily goes in this direction, because this number could be positive or it could be negative. So the current may go in this direction. It may also go in the other direction. This just means that this number is negative. We still keep these arrows, but we allow these numbers to be negative. Now comes the voltage law. If you take such a cycle, any cycle, then you look at what we call the voltage drop around this cycle. And this means, so you choose, for example, the clockwise direction of the cycle, and then you take this current, I5, but you multiply it with the resistance, plus this one, I4, multiplied with the resistance, plus this one, but now we go in the opposite direction, therefore it becomes a minus. Minus I9 times the resistance, and plus, that should be a plus actually, I10 multiplied by the resistance, that should be 0. That should be true for every cycle in the graph. So for this cycle, but also for that cycle, for that cycle, for that cycle. So here we really have a lot of equations. That's many, many equations, exponentially many equations maybe. But this law should also be satisfied for cycles which contain the battery. And here the equation looks a little different. Because now we say, if we take the cycle in this direction here, we take this current multiplied with the resistance plus this current multiplied with the resistance plus this voltage. That should be 0. But now I put this V on the other side of the equality sign. Because now you see what we have. We have a linear system of equations. This is linear. This is linear. And if you just look at these two, it would be homogeneous. You would have 0 here. But then you have these inhomogeneous things with a minus V on the right-hand side. So that's what should be satisfied. This is the mathematical starting point.
How do you treat the battery in the first edition?
In the first here. Well, yes, so the battery we usually draw in this way. So here is the network, and we have the... So this is your question, isn't it? What happens with the battery? Well, I mean, look at this vertex. You count all the outgoing currents. You take the outgoing currents, and they should be equal to the incoming currents. Also, if one of the edges is the battery, because the battery also has a current. The battery has a current also. That was what I called capital I. So, I mean, this edge here could be the battery. I3 could be the battery. So this is an equation for every vertex. Okay. So this gives an interesting system of linear equations, and that's interesting linear algebra to investigate that. I mean, you can make a lot of linear algebra out of this. But the point I would like to make today is that you can also avoid the linear algebra and do it very, very quickly. I'm going to prove that this system of equations has precisely one solution. Precisely one solution. First, assume that there is more than one solution. If you have more than one solution, if you have two different solutions, let's subtract one from the other. It's a linear system of equations, so if you have two solutions, you can think of a solution as a vector and subtract them from one another, then you know we also get a solution. And this is a solution which becomes a solution to a homogeneous system. So that's the case where the battery is zero. Now a physicist would say, now it's clear that this difference must be zero, because if you have a battery with no power in it, there can be no current. But that's a physical argument. We don't accept physics here. We want to do it mathematically. So I'm going to prove mathematically that this solution I'm talking about must be the zero solution. Suppose it's not. So suppose we have a solution where the battery is zero. And so suppose the solution is non-zero. So this means that some current will be different from zero. Assume that it's positive. Assume that the current in edge number 5 is positive. Look at this vertex here. The total incoming current is equal to the total outgoing current. So there must be some positive current going out. I'm looking at a positive current going out. And I can assume that this direction goes as I have said, because I'm allowed to change the directions of every edge if I want to. This is just bookkeeping. The direction of the edges has no meaning except for bookkeeping. So there's positive current going out here. Well, since there's positive current going into that vertex, there will be some positive current going out of that vertex. There will be some positive current going out of this vertex. There will be some positive current going out of this, and there will be some positive current going out of this. So we have positive current, positive, positive, positive. But then look at the voltage drop here. What I called the voltage drop, I mean this current multiplied with the resistance plus this current multiplied with the resistance plus this multiplied with the resistance plus this multiplied with the resistance, that becomes positive. But it should become zero. And that's a contradiction. So this means that I cannot find two different solutions. There is at most one solution. So that was uniqueness of solution. But what about the existence of the solution? Well, this is something that goes back to Kirchhoff. And I think I would like to emphasize this because this is very nice graph theory. I'm now going to give a construction of the solution. I'm going to construct it. Usually when you read about this in electrical network books, you would do some linear algebra and you will reduce the system of equations and you look at the rank of certain matrices, etc. And all that is very interesting, but it's not necessary, and that would be non-constructive. Then you will not know what the current really is. But look, here is the solution. Let's look at any... So I take away the battery. First of all, the battery I don't want to look at. The battery is here. But I don't think of this as part of my graph. I look at the rest, and I take a spanning tree in the rest. When I have a spanning tree, you know that when I have two vertices in a spanning tree, there is a unique path between them. I look at that unique path, and now I send flow through that path. So you know what a flow is. I send a certain amount of flow through every edge here, and I don't send anything through the other edges, just in this path. And the value of that flow is the following. We decide to send this value through the product of all the resistors which are outside the spanning tree. A strange thing. This is very strange. And you may ask, why are we doing this? Well, the answer is because it works. I mean, the truth is the truth, and there is only one truth here, because there cannot be two solutions. There is only one solution. So if we can now find the solution, we are done. So that's what we do. Then we add all these flows together. And whenever, I should say just one thing about the previous transparency. Whenever I have added some flow through here, I send the same flow through this one. So that I really have something where the incoming current is equal to the outgoing current in every vertex. Then I add all those flows together. And as I have already said, I send the flow back from T to S in the battery. And let's see what the flow in the battery then is. Well, every time we look at a spanning tree, we send this amount of flow in the battery. And then we add them up, so we get this expression. And that has a name that's called the network determinant. What have we gotten here? We have certainly gotten a flow. We have gotten a flow from S to T, and then we send that flow back in the electrical network, and that's what we sometimes call a circulation. So it's very clear by our construction that Kirchhoff's current law is satisfied. Kirchhoff's current law, the one about incoming current is equal to the outgoing current, that's satisfied. But also Kirchhoff's voltage law is satisfied, except for the cycles which contain the battery. If you look at a cycle which does not contain the battery, one can see that the sum of, if you take the sum of voltage drops around the cycle, that becomes zero. And that's because of this special construction. It's not difficult to see, but it will take 5-10 minutes to argue. So let me just for the moment say that this is clear, and this can also be proved rather quickly, just 5 minutes. If you look at cycles through the battery, then this voltage law is not satisfied. And it's clear that it can't be satisfied because in the battery we have a number, and that number did not appear in what I did previously. So I must do something to adjust things. But it turns out, and again this can be seen in just 5-10 minutes, that if I multiply everything with this number, then I have the electric current. Then also the voltage law for cycles through the battery will be satisfied. And as I said, this will take a proof of 5 or 10 minutes. Now let's see how much current there is through the battery. This was the amount of current to start with. And then we made the adjustment with this one here, and I've shown that here. So that's the current through the battery. But now remember the definition. The definition of the effective resistance, that was defined in this way. The effective resistance multiplied by the current through the battery is the voltage. But here we have the current. This is I. So I is equal to this, and from this you can find out that the effective resistance is just the reciprocal of this number and this number, so this means this number divided by that number. And now we are going to something completely different. Now you can forget what I have been saying. I'm now going to look at the special case where all these resistors are 1 ohm. What is the network determinant? Oh, I should, did I say what? Maybe I didn't explain what this number was. This is the network determinant for the graph where you have identified the two ends of the battery. So S and T were the two ends of the battery. Now you identify them, you make them into one vertex. And then you take the network determinant of that graph. And remember what the network determinant was. It's a rather complicated thing. For every spanning tree, you take all the resistors outside and you multiply them together. And then you add all those numbers together. So a rather complicated thing. But if you have the special case where all the resistors are 1 ohm, the network determinant simply becomes the number of spanning trees. This means you get the following formula for the number of spanning trees. It's a fraction, and in the numerator, you have the number of spanning trees of the graph, and in the denominator, you have the number of spanning trees in the graph you obtain by identifying S and T. So maybe this still looks a little complicated, but let's look at it in special cases. Let's look at the case when these two are neighbors. I mean, that's a possibility. If you add a battery, you could choose two vertices which are already neighbors to add the battery between. In that case, this number has a very special interpretation. It is simply the number of spanning trees which contain this edge. Let me show you a little picture. If you have a spanning tree and you identify these two neighboring vertices S and T, then a spanning tree in the smaller graph is simply the same as a spanning tree in the big graph containing this edge. That's not so hard to see. Now this becomes very pretty in some special cases. Let me look at what we get in a graph which is R-regular and edge-transitive. Let me explain what these words mean. So R-regular means that all vertices have the same degree, and that degree is R. So it could be 3 regular, or 4 regular, or 5 regular. So 5 regular means that every vertex has valency 5. Edge-transitive, that means that all edges look the same. Whenever you take two edges, you can find an automorphism which takes one edge to the other. So all edges look the same. In such a graph, this becomes very nice, because let me make the summation of all these numbers here. So what we have here is the number of spanning trees containing this edge between S and T. And I make the summation over all the edges. So for this edge, I count the number of spanning trees going through it. For this edge, I count the number of spanning trees going through it, etc. I count a lot of spanning trees in that way. I count all the spanning trees. And look at a spanning tree. It's counted many times. How many times is a spanning tree counted by this count? Well, as many as it has edges. And it has n-1 edges. So this complicated sum is just this number. And that holds for any graph. If it is edge-transitive, then all these numbers are the same. All these numbers are the same. And I'm just adding the same number a lot of times. So I take this number, and since it's the same number for all edges, I put it here. How many times do I get it? The same number of times as I have edges in the graph. And remember, it has n vertices, and all vertices have degree r. So the number of edges is n multiplied by r divided by 2. You remember in a graph, the number of edges is the sum of valences divided by 2. And that's what I'm doing here. But look, this number is equal to that number. And now I can find the fraction of this divided by this. So this number divided by this number, that's the effective resistance. And by combining these two things, you will get this. And this I find very surprising. Because what does that mean? It means that if you have an R-regular edge-transitive graph, and you take two neighboring vertices, the effective resistance between these two just depends on how many vertices there are. Not in a strong way, because this is close to 1. And then it depends on the valency. It does not depend on the structure of the graph, which is very, very surprising. So this is regardless of the structure of the graph. Let's look at some examples, because this formula is very easy to compute, isn't it? Let's look at the cube. The cube up there, that's edge-transitive. It doesn't look edge-transitive in my drawing, but this is the graph of the cube, and you know that in the cube all edges look the same. So we can use the previous formula. This is R regular for R equal to 3. We use the previous formula, and we get the number 7/12. For any two neighboring vertices, the effective resistance between them is 7/12. Let's take the Peterson graph. That's also edge-transitive. Although you may not see it on this picture, the effective resistance between two neighboring points we can find, that's 3/5. And if you take a big cubic graph, the effective resistance is essentially 2/3, regardless of the structure of the graph. What can we say about the number of spanning trees? So, as I pointed out, the number of spanning trees is essential in the theory of electrical networks. If you want to understand electrical currents, you must understand spanning trees. Here is an unsolved problem. You take a graph with n vertices and m edges. I give you n vertices, I give you m edges. You are allowed to construct a graph using those m edges. How many spanning trees can you create? We want to find as many as possible. And you're allowed to have multiple edges. So you're allowed to put multiple edges if you wish to. Usually that's not a terribly good idea, but so here is the result. If n is the number of vertices and the number of edges is precisely n choose 2, then the maximum number of spanning trees you can get is n to the power n minus 2. The best thing is to build a complete graph, a graph where any two vertices are joined by precisely one edge. This is an old result of Kellman's, and he also has similar results if the number of edges is slightly less than this. If you can build almost a complete graph, then, for example, complete graph minus 10 edges, then you can delete 10 edges of a star. You can also delete 10 edges of a matching. And in one case, you will get the smallest number of spanning trees. In the other case, you'll get the biggest number. But I don't remember which is the smallest and which is the biggest. Here is another result on the number of spanning trees. Kostotke proved the following pretty result. Suppose you have a connected graph with these degrees, or valences, d1, d2 up to dn. Then he proved that the number of spanning trees is at most the product of these degrees, and then he could divide it by n minus 1. And he also got a lower bound, which does not look so nice. And this d1, which you see here, that's the smallest degree in the graph. Let's look at a cubic graph. This means that all these numbers di are equal to 3. Then we get something nicer, namely that the number of spanning trees is smaller than this exponential function, but it's bigger than some other exponential function. So for a cubic graph, the number of spanning trees grows exponentially. It's between two exponential functions, and that comes out from this result there. Let me reformulate Kostotke's result a little bit. I don't think Kostotke allowed multiple edges. I'm not absolutely sure about that. But here is the result where we do allow multiple edges. I will call this I'm going to refer to this in the following, and I'll call it the trivial upper bound. The number of spanning trees is at most the product of n minus 1 of the degrees. So this is the product of degrees, except that I have omitted the biggest one. And this is best possible. Oh, so Kostotke's result can't be with multiple edges, because in Kostotke's result, you had a dn here, but then you divided by n. So his result is a little better than what I have here. But mine is best possible. So since his is a little better and mine is best possible, it's because he cannot allow multiple edges. I do allow multiple edges. And it becomes a little prettier when you allow multiple edges, because look at this graph here. It consists of a vertex and then some other vertices which are only joined to this vertex. And if this is the smallest degree, the second smallest degree, the third smallest degree, how do you find the number of spanning trees here? Well, you have to choose this edge, and you choose one of these two, you choose one of these two. That's two choices. Here you have three choices, and you see you get precisely this formula. In this case, the number of spanning trees is precisely equal to this formula. Then we can try to exclude this special situation by assuming, for example, that we have a big matching. This is a graph which only has a small matching consisting of one edge. But if we have a big matching, we can do better. If you have a matching, you know what a matching is. That's a collection of disjoint edges like this. And as you can see, this one doesn't even have a matching with two edges. If you have a matching, then if you look at this product and you look at a matching edge between vertex number I and vertex number j, then you can replace these two numbers by one less. So you get a slight gain here. Let me give you a proof of this, because that can be proved very quickly. Not the matching part, that needs a little longer argument, but the proof without the matching part, that's very easy. Let us say that the vertices are numbered v1, v2 up to vn, and let's say that the vertex vi has valency or degree di. Now I want to consider all the subgraphs which are obtained by selecting precisely one edge incident with every vertex. So I construct now a subgraph in the following way. For every vertex, I select an edge incident with that vertex. In how many ways can I do that? Well, for vertex number 1, I do it for all vertices except for the last one. I don't do it for the last one, but for all the other ones. In how many ways can I do that? Well, if you look at vertex number 1, there are D1 edges I can choose between. If you look at vertex number 2, there are D2 edges I can choose between. And for the second last vertex, there's Dn minus edges you can choose between. So the number of choices is precisely this. What am I counting? What kind of subgraphs am I counting? Well, not very nice subgraphs, but I'm certainly counting something which includes all the spanning trees. Because if you have a spanning tree, you can get it in this way. I mean, if you have a spanning tree, you can draw it in the following way. And you can say that from this vertex you choose this edge, from this vertex you choose this, from this vertex you choose this. So I'm counting the spanning trees plus a lot more. But this means that the number of spanning trees is at most this, because what I'm counting includes the spanning trees and is equal to this. So the number of spanning trees is smaller than this. So that's a trivial proof. And let's look at this formula, what it gives us. Let's have some examples. If you use the trivial upper bound on the complete graph with n vertices, all the degrees are n minus 1. All the degrees are n minus 1, and I'm going to multiply all of them except the last one, then I get this number. It's not the right number. Here we have the right number. But as you can see, if you get these two numbers, can you see immediately which one is the biggest? Because this n minus 1 is smaller than this, but this n minus 1 is bigger than n minus 2. But this one, of course, is the biggest because we have this inequality here. But it seems that, they are similar. They're not that much different. Let's also try the complete bipartite graph. If you use the trivial lemma, then the complete bipartite graph with p vertices in one class, q vertices in another class, and let's say that p is the biggest. Then you get q to the power p times p to the power q minus 1, because you are allowed to leave one vertex out in this formula. So this one is what the trivial upper bound gives, and here is the right answer. It's called Scoine's formula, And you see this one is similar to this one. It's not that much different. So it seems that this trivial upper bound is good for dense graphs. It is not so good for sparse graphs. I don't know if you know the top polynomial. It's a polynomial of two variables, t, x, and y. Whenever you have a graph, there is a top polynomial associated with the graph. I'm not going to say what it is, but it's a polynomial which is very interesting in graph theory. It's interesting in matrix theory, but now it's also interested in physics, in statistical mechanics. Physicists are very interested in this polynomial. It has something to do with the zero state energy of the ferromagnetic thing, and the word Potts model. I've learned a lot of words, but I can't say that I know what it means. I only know that the physicists are very interested in this. And if you put x and y equal to 1, 1, you get the number of spanning trees. So the number of spanning trees can be gotten from this very general polynomial. There are other numbers, interesting numbers, which can be gotten from this, namely the number of totally cyclic orientations. You have a graph, an undirected graph. You put a direction on every edge in such a way that every edge is in a directed cycle. By directed cycle, I mean the following. A cycle where all the edges go in the same direction. That's called a directed cycle. And totally cyclic orientation means that it's an orientation such that all the edges every edge is in such a cycle. And that turns out to be Tg, let's see, 0,2. The top polynomial evaluated at 0.2. And I'm not going to explain what the top polynomial is. Then there's also this number, the number of acyclic orientations. You have a graph and you want to give every edge an orientation. And now you don't want any cycle of this type. It should be acyclic. This means you're not allowed to have any cycle of this type. And the number of such orientations, this is a famous formula by Richard Stanley. That's the chromatic polynomial of the graph evaluated at -1. The chromatic polynomial counts the number of k colorings, with k colors where k is a natural number. That turns out to be a polynomial in k. And this means you can also substitute negative numbers. You can't color a graph with a negative number of colors. But nevertheless, this turns out to have a very interesting interpretation. It's the number of acyclic orientations. Another interesting thing, it's the top polynomial evaluated at 2.0. So look at these three points, 1, 1.1, 0.2, 2.0. And you see 1.1 lies in the middle of the line between 0.2 and 2.0. I mean, if you have the coordinate system here, you have 1.1 here, you have 2.0, and you have 0.2. I mean, 2.0, 1.1, 1.2. The number of spanning trees lies just between the number of acyclic orientations and the number of totally cyclic orientations. Is there some connection here? Is there some explanation of this thing? Or you could also say, are there some relations between the number of spanning trees, the number of totally cyclic orientations, and the number of acyclic orientations? Well, here is a connection. The first connection I would like to mention. Let's look at the number of spanning trees in a graph. I think you'll agree that there are two types of spanning trees. If you take an edge E, then there are those spanning trees which do not contain the edge E, and that's this number. And then there are those edges which do contain, those spanning trees which do contain the edge E, and that's also the same as the number of spanning trees obtained by identifying the ends of E, or contracting the edge E. So if you have X and Y, that's the edge E. Then contracting this edge E means that you make this into just one point. And then you have this nice recursion formula. And using this, you can compute the number of spanning trees in an arbitrary graph. It will take a long time if the graph has many edges, because this computation turns out to be exponential. But if it's a graph which is not too big, you can do it. It's very useful for small graphs. Well, we have exactly the same recursion formulas for the number of acyclic orientations and the number of totally cyclic orientations. The same formulas. And now you may ask, but if we have the same recursion formulas, why are these numbers not the same? Well, because you have to add a little bit. These formulas hold for sure if E is neither a loop nor a bridge. So these two formulas, you can only be sure that they are true if E is not a loop and not a bridge. And if you look at the graph just consisting of one bridge, the graph with one edge and two vertices, or the graph consisting of one loop and one vertex, let's look at that graph. Well, how many spanning trees does that have? It has one spanning tree. How many acyclic orientations does it have? Well, it has two orientations, and each of them is acyclic, so that's two. How many totally cyclic orientations does it have? Well, we want this edge to be in a directed cycle. That's not possible, so the number is zero. What about a loop? There's still just one spanning tree, namely the tree consisting just of this vertex. That's a tree. How many acyclic orientations? None, because whenever you give this an orientation, you have a cycle. How many totally cyclic orientations are there? Well, now there are two, because now you can orient this in this direction. You can also orient it in the other direction. Two cyclic orientations. So you see, although these have the same recursion formulas, they start in completely different ways. And that little difference here, which looks innocent, I mean, that becomes enormous when the graph is big, even if they satisfy the same recursion. But still, are there some connections? Here is a conjecture of Marino and Welch. They conjectured that if you look at these three numbers, the number of spanning trees, the number of acyclic orientation, and the number of totally cyclic orientations, then, well, one of these two could be very big and the other one could be very small. But they believe that one of them will always be bigger than the number of spanning trees. So if you look at the top polynomial defined on this line, just look at it as a function of one variable defined on this line between 2.0 and 0,2, then this is the beginning of some theory of convexity. Convexity for a function. But it's still a conjecture. We don't know if it's true. Let me point out that if you have a planar graph, then if you have a graph drawn in the plane without edge crossings and you take the dual graph, then the number of spanning trees in those two graphs are precisely the same. But if you look at the number of acyclic orientations in one of them, it becomes the number of totally cyclic orientations in the other one. So that's another nice relation between these two numbers. And there you can see that if you have a planar graph and, well, for planar graphs, it would be sufficient to prove this either for the graph or its dual graph. You are allowed to switch between the graph and its dual graph. But I would like to now talk a little about this conjecture. So the number of spanning trees should always be smaller than at least one of these two numbers. I have proved this for many graphs. I have proved it for graphs whose number of edges is at least 4n minus 4. So n is the number of vertices. And if you have a dense graph, and it does not need to be very dense, the number of edges should just be bigger than this, then it's true. And then I have also proved it for graphs whose number of edges is at most this. So this means it's almost proved. The only thing that remains are graphs whose number of edges is between this number and that number. Well, which graphs have that property? For example, the cubic graphs. If you take a cubic graph, the number of edges is the number of vertices multiplied by 3 over 2. So 3 over 2 is between these two numbers. But I can also prove it then separately for cubic graphs. And if it's true for all cubic graphs, it's also true for all planar cubic graphs. And then it's also true for their dual graphs. That's the planar triangulations. So I can also prove it for planar triangulations. So there are many graphs for which it's true. But the problem is still open in this little gap here. So maybe I can say a little about this. Let me first say a little about the number of totally cyclic orientations. Remember, this means an orientation such that every edge is contained in a directed cycle. If you have n vertices, now I'm looking at a bridgeless graph. Do you remember what a bridge in a graph is? For example, if you have this graph here, then this edge is a bridge because it has the property that if you take it away, you make a disconnected graph. So that's called a bridge. I want to look at graphs which do not have such edges. They are bridgeless. Another word is two-edge connected. Let's assume that it has m edges and n vertices. Now the number of totally cyclic orientations is at least 2 to the number of edges minus the number of vertices plus 1. And this is trivial. Because let's first look at a cycle. How many totally cyclic orientations does a cycle have? Well, there are two ways. I mean, every edge should be in a directed cycle. So if this edge is like this, then all the other edges should be directed like this. So that's one totally cyclic orientation, and then you can reverse it and let all the edges going in the other direction. But there are only these two. But let's look at this number here. When we have a cycle, well, then these two numbers are the same, and we just get the number 2, and that's okay. So the number of totally cyclic orientations is at least this when we have a cycle. When we don't have a cycle, now we are going to use induction. If you have a bridgeless graph, which is not a cycle, then it can be obtained from a cycle by the following operation. You add a path, you add a path which could be a cycle, you add a path, you add a path, you add a path. It's clear when I do this operation. So I have a current graph, and then my operation is I add this, then I still get a bridgeless graph. Conversely, if I have a bridgeless graph, it can be obtained from a cycle by using this operation. And the proof is not difficult. The proof is rather easy. I'm not going to give the proof, but it's certainly not difficult at all. Let's see what happens if we have a totally cyclic orientation here. In how many ways can we extend it to this? In 2 ways. Because we can let all the edges go like this, or we can let all the edges go in that direction. That's 2 ways. So this means when we go from here to here, the number of totally cyclic orientations increases by at least, it's at least doubled. It's at least doubled. Maybe it's more than doubled because I don't have to start with a totally cyclic orientation here. But now I decide to do, and therefore I can say that the number of totally cyclic orientations at least double when I do this. What happens with this number? Well, here you have the difference between the number of edges and the number of vertices. What happens with that number when I make this operation? Well, let's count. How many edges? I add 1, 2, 3, 4, 5. How many vertices do I add? 1, 2, 3, 4. 5 edges, 4 vertices. So this number increases by 1. But this means that this number increases by a factor of 2. It's precisely doubled. And therefore it's true what I'm saying. Because this number increases by it's precisely doubled, and this one is at least doubled. So it's true, by induction. So we have proved this little thing by induction. Now let me show that if we have a bridgeless graph with n vertices and m edges, and m is at least this, then the number of spanning trees is at most the number of totally cyclic orientations. So this is a contribution to the Marino-Welch conjecture. And with the things we have established, it's very quick. It goes very quick. Because here, remember, we have the trivial lemma. And it's still true if I add the last degree, isn't it? I mean, if I have an inequality and I add the last degree, it's certainly still true. And what can we say about this product? Well, we know that the sum, we know what the sum of these degrees is. That's twice the number of edges. And the average, therefore the average of these numbers is the number you have here. Twice the number of edges divided by n. And if you want to maximize such a product of numbers whose sum is given, then the best thing is to make them the same size. Then you maximize such a product. So you maximize this by letting all these numbers be approximately the same, which could be this. So you get this nice formula. And then when I did this this morning, I wrote smaller than 8 to the power n minus 1. And that's incorrect, because you see, we say m is bigger than or equal to something. And therefore this inequality goes in the right direction. But let me nevertheless keep it. This is what I have just proved. This is what I have just proved. So you see, this number is the same as that. And this number is bigger than this, and this number is smaller than that. So I have finished. But there's one little trouble. This is, I realized this morning, this inequality goes in the wrong direction. So that worried me. Is the whole thing incorrect? No, because fortunately, you should just read it in a different way. This is true when, this thing here is true when n is equal to 4n minus 4. And so these two inequalities, this inequality and this inequality, they are true when n is equal to 4n minus 4. In fact, that's how I found this function. That was by this thing here. So for n equal to this, this number is smaller than that number. Then when you let m grow from this number and upwards, then you'll see that this grows slower than this, because this is an exponential function and this is only a polynomial. So therefore it is true. It is true. And it's just a few lines. I don't have too much time left. So I should not continue too long. I should probably stop in 4 minutes. Is that an appropriate time to stop?
Yeah, or you can take a bit more time if you want.
So let's see.
You won't fly to computer. Why not just add more time for you?
Okay, so yeah, so I think I will skip the proof of cubic graphs. Maybe I can show it. It's only 2 transparencies. Let's assume that we have a cubic 3-connected graph. It's important that it's 3-connected. Otherwise, what I'm saying now is not true. If you have a cubic 3-connected, so cubic means that every vertex has degree 3. 3-connected means that if you want to disconnect it by taking vertices away, you have to take at least 3 vertices away. Every cubic 3-connected graph can be constructed in this way. You can start with a cycle, and then you can add paths, a path like this, a path like this, a path like this, a path like this, etc. Well, so far it is just a repetition of what I have already said. But now I'm saying a little more. These paths, this construction can be chosen in such a way that all these red paths, which have length R2, R3, etc., all have length at least 2, except the last one. When I put the last one in, that will just be an edge. But all the other ones can be chosen to have length at least 2. And that turns out to be interesting in connection with acyclic orientations. Because if you look at a cycle, how many acyclic orientations does it have? Almost all orientations are acyclic. You have R1 edges, and you have this many orientations, and there are only 2 of them which are not acyclic. So you have this many acyclic orientations. And if you have an acyclic orientation here, and you add a path of length at least 2, then you get, again, you can extend that to, you can look at all orientations of these edges, and there is only one which will give rise to a cycle. So you get at least that many extensions to acyclic orientations. And look at this number. If Ri is equal to 2, no, if this one is equal to 1, then you get 2 minus 1, which is 1. And that is not good, because this means I don't get anything extra going from here to here. But if this number is at least 2, then I get at least 3 here. So this is completely different because I do it many times. And this means that the number of acyclic orientations can be written as at least such a product. I know how many elements there are in this product. That's just because I know how many edges a cubic graph have. And I know when I add this, the difference between the number of edges and the number of vertices increases by 1. And that will happen precisely this many times. I also know what the sum of these is, and now I can start minimizing. And it turns out that I minimize this when the R1 is a big cycle and all the others just have length 2. And then I get this result. A cubic 3-connected graph has at least this many acyclic orientations. In my proof, it's important that it's 3-connected, because if I only have 2 connected, then my proof doesn't work. But it turns out that if I could extend this from 3-connected to 2-connected, I will have a best possible result. Then this 6 to the power n over 2 will be best possible. So I'm not far from best possible here. Well, let's see how far I am with 3-connected. Look at this ladder here. One can prove that it has precisely this many acyclic orientations. This is just simple counting. You can do that by induction, because you can see what happens if you add if you make the ladder a little bigger. But this is not cubic. So what I do now is I add this edge and this edge, and now it's cubic and 3-connected. And what happens with this number? Well, it becomes bigger, but not much bigger, because this can only be oriented in 2 ways, this in 2 ways, so the number of acyclic orientations will be at most this multiplied by 4. So it will still be 7 to the power n over 2, multiplied with a constant. So this is what I proved, and nobody can prove better than this. So I'm rather close to best possible here. And I would like to pose the following problem. Is this the best construction? Can somebody find a cubic graph which has this many acyclic orientations, more than this many acyclic orientations, and in order to exclude some small counterexample, I multiplied by a polynomial. So I'm asking, is the number 7 here essentially best possible? How does this relate to the Marino-Welsh conjecture? Well, here are some beautiful theorems of Brendan Mackay. He proved that if you have a cubic graph with n vertices, then the number of spanning trees is at most this number. Another way of saying this is that the maximum number of spanning trees, if you take the nth root of that, that will converge to this number, which is 2.3 something. He also proved that the same thing happens with the average number of spanning trees. It also, when you take the nth root, will converge to this special number. And then when you compare it with the result I mentioned, you remember the 6 to the power n over 2, then it follows that if you combine this with Brendan McKay's result, the maximum number of spanning trees will be at most the minimum number of acyclic orientations for cubic graphs. So every cubic graph will have a number of spanning trees which is smaller than the number of acyclic orientations. But here we have a stronger result, namely that if you take the maximum over all cubic graphs, and if you here take the minimum over all cubic graphs, you still have this inequality. So this is the conjecture in a rather strong version. But it only is true for n greater than 28, unfortunately. So what do we do for n smaller than 28? Well, I asked Gordon Royal to help me. And he could help me up to 22. He could actually find the maximum number of spanning trees, and his numbers are all a little smaller than my numbers. My numbers are just a little bit bigger than his numbers. Then I had a problem with 24 and 26, and I asked Brendan McKay, but then he said he could improve his theorem a little bit, get a little better for those two numbers. And then we are below my number. Now we have the theorem for all cubic graphs. Thank you very much.